afternoon and welcome to Adventure. We're going to be learning about ocean acidification with Harbor Wild Watch today. So as you start tuning in, if you could let us know where are you tuning in from and what grade the students tuning in with you are, that would be so excellent for our grant purposes. I will also go over some materials that we'll need for today's ocean acidification experiment. So if you would like to do a hands-on experiment along with me, some things that you will need include vinegar, containers, whatever those may look like. You can use cups, you can use these little dishes. I'm going to use an ice cube tray. That lets me put a variety, oh let's see, can I do this without spilling it everywhere? A variety of different things that I think might react with vinegar. So I'm thinking about what are some things that might have calcium carbonate in them, and what are some things that maybe don't. So I have tums, I have this piece of, oops, it's all backwards, limestone, some plastic beads, wood chips, various types of sand, coral shells, just kind of a nice smattering of things that I'm curious to test as to whether they contain calcium carbonate or not. So really, if anything you want to give a try, we're going to add vinegar to them to see if they show signs of dissolving. So pick your poisons, call it good. And I also have a little pipette. If that's not something you have lying around the house, you can just simply pour vinegar into the cup. That should work fine, but I kind of like the sciencey feel of using a pipette here. So once you have those materials ready, and again, if you're just tuning in, if you could tell us where you're tuning in from and what grade the students tuning in with you are, that will let us get started. So to begin, we're going to kind of be doing some acid-base chemistry. Now, I won't get too wild into the chemistry weeds, but it is good to understand what's the difference between an acid and a base and kind of take a look at the pH scale. So I'm going to pull up one for you over here, and we'll pop over. For some reason my tripod is not holding very steady. Alright, we can also put this in the comments, but the pH scale, I like to think of it as the power of hydrogens, and this is a scale that measures the number of hydrogens in a substance. And so neutral would be 7, and the lower the number, the more acidic the item, the higher the number, the more basic. And another way to kind of think about that, other than looking at the common household items, like things like a lemon would definitely be on the acidic side of things. Things like bleach would be more basic. But if I were to just really simply look at this, that neutral 7 in the middle would be pure H2O. So you might recognize that as the formula for water. And so there's an even amount of hydrogen ions, which would be the H+, and our hydroxide ions, so the OH-. And so when you have H2O, there's a perfect balance of what you can see here is the red and the blue. And as even just one extra on either side will start flipping you to a more basic solution if you have more hydroxide ions, or a more acidic solution if you have more hydrogen ions. So with that in mind, it's kind of, oops, we'll get to that later. It's an interesting thing we can do is we can actually change the pH of water using our breath. So every time I inhale, breathing in air, can anybody answer in the comments, what is the gas that I'm exhaling? It has a certain name. So if I breathe in and then I exhale, it's what plants use to carry out photosynthesis. If you said, actually, I don't even think I have the comments turned on. For some reason that's not working on my end. Anyways, I think Carly's out there running tech for me, so hopefully she's out there responding to your comments, because for some reason I can't see what you're saying out there, so sorry about that. But as I exhale, I'm breathing out carbon dioxide, and that's something that not only our breath releases, but when we burn things like fossil fuels, carbon dioxide is something you'll see. So, oh, now my comments are working. So CO2 is absolutely a shorthand way of, or an abbreviation for saying carbon dioxide. So you said that, good job out there. So what I'm gonna do is a little bit of a demonstration of this before we talk more about ocean acidification. And then we'll get onto that experiment that I mentioned earlier. So first I'm gonna take just some regular old tap water, and we have an aquarium here at Harbor Wild Watch, and the water quality is pretty important. So we have some just simple testing things. One of the things we test is acidity, because if our water isn't in the right balance or range, our animals aren't too happy about that. So I have this plain water in one of my vials, and then I'm simply, gonna throw things on the ground. All right, I'm gonna take a straw, and from that same little container of water, I'm gonna blow into here. So maybe about 20 seconds of adding some carbon dioxide with my breath. While I do that, maybe you can make a prediction. Is my breath gonna make this water more acidic or less acidic? We'll have that original water sample to compare to. So, ready? I wonder, maybe I'll do one more breath just in case, but it'd be interesting to do a tiny breath, a longer breath, and a bigger one, but maybe we'll save that demonstration for another day. But here's one more. Okay, I think that should be good. So now I'm gonna take our water plus carbon dioxide. We're gonna fill up another little vial. If you have an aquarium at home and you have your own set of pH kits, you're welcome to try this out too. And then I'm gonna do a third test. Since I have this nice vinegar here, let's see what one with vinegar looks like. And what I'm gonna do is I'm gonna add a little color changing solution that we would use for our aquarium. And the way the color changes for these samples will tell us what the pH is of this water. So my prediction would be that the vinegar is probably the most acidic, tap water the least, and this water plus carbon dioxide somewhere in the middle. So to find out, we're gonna add 5 drops of our little pH solution tester here. So 1, 2, 3, 4, 5 for our water sample. We're gonna shake that up soon. Let me see if I can. It's kind of hard to get all the things in the screen correctly. Sorry about that. All right, and then our water plus carbon dioxide. You can count with me. 1, 2, 3, 4, 5. You might make some observations as we go along. See if you notice anything as we add those drops of color. And then for our vinegar sample, ready? 1, 2, 3, 4, 5. All right, now this is important. We gotta shake it up. So if you're out there and you'd like to shake it with me, here's our vinegar sample. So there's one color I'm starting to see. Here's our tap water sample. Ooh, very different. And then our sample that has carbon dioxide on my breath, plus just the water. It's different. So if I compare all three of them, it's kind of loud. Okay, I clearly need to be an octopus because I need one more hand to do this. All right, so we have vinegar, our breath, and the water. So you can see, kind of definitely, I would say my prediction was right. I'm gonna see if maybe I can put it against the white. There you go. So you can see the blue color. I'm looking for my little pH range kit. Normally I have a little card that says what it would give me a prediction about the number, where on that scale it would be. And I know it goes from kind of the cool colors to the warm colors as you get more acidic. And so that vinegar can definitely be the most acidic, whereas that tap water's probably pretty close to neutral. And then our breath definitely increased the acidity of our tap water. Now, the same thing happens as fossil fuels are burning in our daily day-to-day activities, and that carbon dioxide actually mixes with the ocean, and the ocean is amazing because it acts like a carbon sink, and essentially will absorb some of that CO2 rather than letting it all accumulate in our atmosphere and kind of act like a warming blanket for our globe. Now, as those greenhouse gases, which CO2 is one of, increase, that causes our climate to change. And in general, it has a warming trend. And so a warmer ocean, just like a warm soda, isn't able to hold as much gas. And so it can't absorb as much of that CO2, kind of being that buffer protection from all the greenhouse gases in our environment that causes our climate to change. So there's this really kind of, amazing, beautiful reaction or connection between all these things, how the ocean helps keep our atmosphere from keeping our planet too warm. So with all of that combined, I'm gonna put a little video in the link that I think does a nice job of explaining ocean acidification and climate change in general. It's a nice little animation that you can look at later. But this ocean acidification, or the warming of our seas, which then we have the calcium carbonate that are our shell building materials, that carbon dioxide and those little hydrogen ions that are reacting off of that are going to actually interact with those shell building materials and make them less available for our shell building animals out there. So in addition to kind of worrying about our easy to crack clams, a lot of people rely on the ocean as a source of their protein. So less food for us, and then less food for the animals out there that need clams to eat, as well as other shell building animals, kind of gives us a little bit of, or plenty of concern about the health of our seas. And so what we're gonna do is kind of demonstrate an extreme version of ocean acidification, because of course, if we were to test the pH of the ocean, it would not be as acidic as this vinegar here, but there's definitely a threshold where it's not possible for, especially like baby larvae of things like oysters and clams, they become deformed if the pH isn't quite right. And I think I'm going to show you this last little picture of a little shell building friend that I fondly refer to as the potato chip of the sea, also known as a pteropod. It's a little snail with this round shell here, curls around just like a snail you might imagine, and it is a food source for all sorts of things, including salmon. And in a nice non-acidic environment, those shells can build and be nice and happy, but there's definitely some pretty sobering experiments that show what would happen to these little shell building mollusks if climate change is left unchecked and our seas continue to become more acidic. So it's not looking very happy for that little shell builder out there. So we are going to shift gears to our vinegar experiment and see what a more extreme acidic environment might do for those materials that you might predict have calcium carbonate in them. So I have a nice little chart ready for us to use. And if you'd like to gather your supplies, I have some vinegar ready. I'm trying to see how I can get a good angle because for whatever reason this tripod keeps rolling on me. So I'm going to try and pin this. Doo-doo-doo-doo. I don't know why that's trying to raise up. Let's see. Okay. One moment. Do a little finagle in here. All right. Well, yeah, I don't know why. Anywho, let's try this out. I misplaced my pipette, team. Aha! Okay. So, we are going to first, of course, as good scientists, make some predictions. I'm gonna write either a yes or a no next to things I predict will dissolve as we add some vinegar. Shell, I'm gonna say probably yes, because I just talked about ocean acidification and the trouble that might cause for our shell builders. I'm gonna say yes, that's likely. Plastic, I don't think that will dissolve in acid, mostly because I'm thinking about the plastic holding this jug of vinegar. It's doing just fine, so I think that's okay. Coral, I'm definitely in relation to those shell builders, so I think that one will probably have some calcium carbonate. Aragonite sand, this is essentially sand made from limestone, and limestone is a sedimentary rock that is formed in some cases from layers of coral or coral sediment from old reefs back in the day, and those sediments of coral formed layers, and a chemical reaction combined those layers into rock called limestone. So I think if aragonite sand is connected to that, yeah, that's probably going to dissolve. Silica sand, I think that's made out of, silica is like glass. So again, I would store acids in glass. So I think that'll be okay. Wood chips, ooh. I'm gonna say no. And chalk, probably. Limestone, sure. Tums, I use that for heartburn. I know that if you're reacting a base with an acid, the acid reflux, then hopefully it will dissolve down. So those are my predictions. Hopefully you have a chart of your own out there and you're ready to test whether these materials contain calcium carbonate or not. And again, to do that, we're just gonna add a little bit of vinegar to each one and make some observations about whether or not we notice any signs of dissolving. So I'm gonna start with our shell builders here. So I have some shells, and we're just gonna add some vinegar. And right off the bat, I'm noticing some bubbles. I can't quite tell if that's from my powerful pipetting or if there's something more going on. I let that sit for a little bit. Ooh. Bubble out of nowhere. Okay, so it's not a, those definitely enough bubbles to make me think that something is happening. So yeah, and if I look closer, what I think my camera can't really capture is that there indeed a little lining of bubbles all along these shells here. So while they're not dissolving very quickly, there is some signs of dissolution here. So we can definitely mark maybe dissolving slowly as our observation for the shells. Next, we're going to add some vinegar to the coral. In the comments, you don't have to agree with my predictions. What do you think is going to happen when we add vinegar here? Do a couple squirts. I'm going to look at what I'm doing because it's hard to function backwards with you. Okay. Coral's in this container here. And just like those shells, I'm seeing some small bubbles. You're welcome to share any observations you notice in the comments. Reacting again very slowly, but I'm seeing a reaction there. Now I'm gonna keep this here because when we add some vinegar to our aragonite sand, make sure you can see that. That is bubbling fiercely. It's reacting. And part of what makes this aragonite sand react so aggressively with that vinegar is it's sand, so with calcium carbonate bits, essentially crushed shell, crushed limestone, and because there's so much surface area on that sand, there's a lot of area for that acid to react. And as the acid reacts with the calcium carbonate, or it releases carbonate, just like a carbonation kind of, you can think of that. So definitely a big reaction there. Next I'm gonna try our silica sand. I was kind of expecting a similar thing almost, but yeah, nothing. I'll add a little bit more. Oops. Stir it up a little. I'm not even seeing tiny bubbles. Oops. Sorry about my operating backwards here. That's aragonite sand is still bubbling. Well, I don't see any signs of bubbling on our silica sand. Next we'll try our wood chips. Any signs of bubbling there? Not surprising that a tree might not contain any calcium carbonate here. I'd be curious if there are some plants that contain something that would react, but not this one today. Let's see, let's try that plastic. Kind of going with our unreactive things. There's some just little pink pony beads here. And again, not much happening there. I'm a little curious about the chalk. So this is just some sidewalk chalk that is replacing another version of chalk that we had. And while chalk back in the day was made from tiny little animals called coccolithophores, today's chalk is more of a processed variety. So I'm kind of curious if this chalk will even react at all. So let's find out. I need to pour myself some more vinegar because I would like to submerge this chunk of chalk in the acid. Pour this in. Not seeing a ton of reaction there. So that could let me know that this chalk is not the chalk of coccolithophores. It is, I have no idea. I'll have to look at the ingredient list. That could be interesting. I'd be curious to see if there's some chalks out there that do dissolve more or have a bigger reaction. So this one definitely, well, I guess, okay, I'm seeing a couple bubbles. Not a lot going on there. How about this limestone? Let's take a look at that. hold that a little full. All right, the limestone. Whee. It's got some tiny bubbles starting to form. Again, the surface area on the limestone is not as great as the sand. It's kind of one big chunk. It's pretty solid, but you can definitely see some tiny bubbles letting us know that indeed that limestone could be made from the coral of a past coral reef layered into sediments, forming into this version of sedimentary rock. And then finally I have a nice antacid here. Let's see if we get some pink foam. Da 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 da. I'd be curious if I chewed up the antacid tablet, how that would make a difference. It would make it kind of slobbery, probably. Not COVID safe, but definitely can see some bubbles there. So calcium carbonate in that material, which will help relieve your acid reflux happening in your body. I sure am thankful for our tums. Cool. Well, I didn't keep up very well with my graph, so let's do some ketchup. Plastic, no dissolving. Check. Coral, some slow dissolving. Aragonite sand, very much. Silica sand, nope. Wood chips, no calcium carbonate there. Chalk, I'm gonna say no for this one. We might have to try a new type of chalk to get some dissolving. Limestone, yes, although slow. Tums, yes too. So if you end up with a nice graph or chart that you can then graph, showing the results or things you've tested, wondering if they have calcium carbonate. I know we have some shark teeth somewhere. That would be kind of a fun thing that I'm thinking, okay, if my teeth have some calcium as part of them. Granted, they are protected in a strong enamel that will hopefully keep them from dissolving, but there's definitely a reason why you don't want to brush your teeth and then drink things like coffee or soda, because by brushing your teeth, you're kind of I guess roughing up your enamel surface, making it a little more exposed to acids. So once you brush your teeth, it's a good time to just go to bed, I guess, or start your day. Don't drink things like juice or coffee right away. Let your enamel settle back in. With that, thanks for trying out this pretty simple experiment here. Again, if you have any observations or results or things that you like to test, we're always curious in improving our lessons, and so we might have to add whatever material you tried out to this fun experiment. I'm gonna flip back to our ocean acidification first slide here. Shift some of these liquids out of my way. So again, just to kind of relate back to this vinegar reacting with those things, we can look at this graphic again. So again, the carbon dioxide that reacts with our ocean releases those carbonate ions, and so with more carbon dioxide in our water, that increases the acidity of our ocean, and with more acidic ocean water, those shell builders again are not gonna have the most pleasant of times. So I'd be curious in the comments if y'all can maybe share some solutions, and if you're thinking back to our experiment where I breathed CO2 in the water. I'm crossing my fingers that you all don't say stop breathing, because we definitely need fabulous stewards like you out there making the positive changes that I think you'll suggest in our comments. So keep breathing, even though yes, that does increase our CO2, but I think it balances out with the plants, which of course are another carbon sink, because plants are taking that carbon dioxide in and releasing oxygen for us to breathe. So there's absolutely a nice balance and cycle there, but when we're out there burning too many fossil fuels, that definitely can kind of tip the scales, and the animals don't have enough time to adapt to such a increase in this change. And so while if change was happening more slowly, these creatures could slowly adapt to that and make the changes necessary to survive and thrive. These changes are happening kind of at an unprecedented rate, which makes it impossible for these animals to evolve to combat the impacts that we're seeing from climate change. So we look forward to doing some more lessons with you all regarding climate change and ocean acidification, but this is just our little toe dip for now. And of course, with that, I'm going to go ahead and wrap up for today and look forward to having you join us next time. If you enjoyed watching this video, definitely consider following us on Facebook as well as Instagram. You can even subscribe to our YouTube channel. And if you click the little notification bell, you can stay updated for when Harbor Wild Watch releases new content. We also have a Steward Club, which gives you access to exclusive content, including our newsletter, which I think we're just about to send out. So if you sign up soon, you'll be in on our next one. And of course, that Steward Club supports Harbor Wild Watch and lets us keep creating this new material that we're putting out online. So we appreciate all our Steward Club members out there and look forward to having more of you join our team. And of course, you're welcome to share this video. That's an easy, free way to support Harbor Wild Watch. And if you feel so inclined, I see some folks, you're so sweet out there for donating on this link. You can also donate on our website to keep supporting Harbor Wild Watch's mission of inspiring stewardship, learning, and having fun. And with that, we look forward to having you tune in again. I know I'll be doing a sea star survey next week as part of this lesson, so tune in for that fun community science adventure. And with that, thank you so much for watching, and